So in part 2, we will discuss the generation of action potentials. This is what we just discussed, actually, where we ended the last screencast with an expression of the membrane voltage given by basically a weighted sum of the Nernst potentials. So this is the Nernst potential of sodium, the Nernst potential of potassium, the Nernst potential of the leak currents. They need to be multiplied with their conductances and divided by the sum of the conductances. And that will result in the resting membrane voltage. Now, the interesting part of biological cells that also gives rise to interesting dynamics is that the conductances are not constant. So the sodium and potassium conductances in particular are a function of the voltage. And that was quite a discovery made around 1945, 1950, 1960 of the last century by Hodgkin and Huxley, and they eventually were able to make a very explicit expression for the membrane voltage. Now you can already imagine, if you play with the conductances here, if you change their value, for instance, you increase the sodium conductance much more, make it much larger than the potassium conductance, then the membrane voltage will tend to go to the sodium Nernst potential, while if you increase the potassium conductance much more than the sodium conductance, then the membrane potential tends to go to the Nernst potential of potassium. And as the concentrations of those two ions are basically opposite, the membrane potential can indeed change from, say, minus 60, minus 70 millivolt to plus 60, plus 70 millivolt. So we'll look a little bit more in detail how this process can be understood and described. So we'll start with our electrical circuit of the cell membrane that actually was the result of all the experiments that Hodgkin and Huxley did, but we will start here with the circuit for our discussion. And in fact, Hodgkin and Huxley had some idea that this would indeed represent the properties of the cell membrane. So shown again, the membrane capacitance, the leak conductance, and the leak Nernst potential, and the two relevant voltage voltage-dependent currents, the potassium current and the sodium current with their respective Nernst potentials. Note the opposite position of the two batteries, as the potassium and Nernst potentials have opposite signs. Now, how can you get more information about the currents in the circuit? Well, one of the things you can do is that you apply an external current and you measure the external current, and at the same time record the voltage across the circuit. Then indeed you can get an impression of the, say, composite currents through all these four legs. But if you're interested in the potassium current only, or the sodium current only, and that was indeed the question Hodgkin and Huxley asked themselves, then you need to find a way to separate those four currents. And at the same time, you like to keep the membrane voltage constant. Now that was really a challenge. So you need to separate currents and at the same time keep the membrane voltage at a constant value. Now, as a recap, we can write the external current as the sum of all the currents in the circuits, shown here, the potassium, the sodium, the leak, and the capacitive current, and that can all be also be expressed in this way. This is basically Ohm's law, the conductance times the voltage difference across the component at hand. And for the potassium current, here the current through this resistor or conductor is given by the difference between the membrane voltage and the Nernst potential of potassium, and the same applies for sodium and the leak current. And the capacitive current, we discussed this already, is given by the capacitance times the time derivative of the membrane voltage. Now, as already said, and if it's not clear yet, it will be clear shortly. It was very important to do these experiments to keep the membrane voltage of the axon, and this is what Hodgkin-Huxley studied, constant. And that was a non-trivial experimental accomplishment. And they were very lucky that eventually they were able to do experiments in the giant axon of the squid, because first of all, that axon is large. The diameter is approximately 1 millimeter, which is very, very large for an axon. And this is how the axon looks like. This is about 1 millimeter. And they were able to insert an electrode in the inside of the axon. And at the same time, they were able, I will shortly show that, to keep the membrane voltage constant. And they were also very lucky that in this particular axon, there were basically only two relevant ion channels, sodium and potassium ion channels, no chloride, for instance. And that made some of the experiments much more accessible. So what is a voltage clamp? Well, it's a technique to keep a transmembrane voltage to a preset value. So what is shown here is a differential amplifier with a control voltage. And as you know, that the differential amplifier has as a task that it wants to keep the two inputs at the same voltage. Now the output of this differential amplifier controls a current source which injects current into the axon, and there's a recording electrode that records the voltage of the axon, the transmembrane voltage, which is fed back to the input of the differential amplifier. So the differential amplifier will make the current, will make the current so large, will set it to a particular value that indeed the membrane voltage will be exactly the same as the set voltage. So this allows you to measure a particular current through the membrane that is needed to keep the membrane at a particular voltage. Now this is called voltage clamp. Now we'll go back to our circuit. And why is voltage clamp so present? Well, what you can do is that you can apply a particular voltage to this circuit and keep it at a particular value. And while that is the case, there's no change in the voltage, so there's no capacitive current. So this simplifies our expression already, because this term can be removed at the steady state, of course, here. That was step one, eliminate the capacitive current. The capacitative current. As a second simplification, and this is mainly for teaching because it's not completely what Hodgkin-Huxley did, but for the sake of the argument we can now do this. We can ignore the leak current. So we are left with an even simpler equation displayed here, where the external current is essentially the sum current of the potassium and the sodium currents, expressed here again. And now the voltage clamp is reintroduced again. So what Hodgkin and Huxley did, they applied a particular voltage to their membrane, and they waited a little bit after the voltage step, and they were able to record the total current, because that was the current to keep the membrane at that voltage, which equals the sodium and the potassium current. And that sum current is displayed here. So when the clamp voltage is set to a particular value, this is the total current that needs to be injected into the membrane, which is essentially the sum of the sodium and potassium current, which is associated with a particular membrane voltage. But note that this is a sum current, so it's the potassium and the sodium current, likely. And we wish to separate the two currents. Now, a very smart way to do that is to change, for instance, the extracellular sodium concentration to that value where the Nernst potential of sodium has the same value of the voltage clamp. So you set the axon transmembrane voltage to a particular value, which is exactly the same as the Nernst potential of sodium. Now if you do that, then this term is 0 because there's no current. Because the Nernst potential of the sodium is exactly the same as the membrane voltage that is set by the experimenter, and then indeed there's no current in this lag. So if you repeat the experiment with this other sodium concentration, the same voltage clamp experiment, and you measure again a current, then you are sure that that is only the potassium current, and that is shown here with a dashed line and the 10% sodium. Now then, of course, assuming that all the other conditions have remained the same, you can subtract those two currents from each other, and then you will have the current that was originally present in this lag of the circuit only, which is the sodium current. So now we have separation of currents. This is the sodium current, and this dashed line is the potassium current. Now that's very smart. And what is immediately shown is that the potassium current, the dashed line here, is a persistent current. As long as the voltage of the membrane is set to this value, there is a current, and the channel remains open, therefore, while the sodium current initially has a finite value, and then eventually decreases back to 0. And note that the sign is different from the potassium current because of the fact that the Nernst potentials have opposite signs. Now you can repeat this experiment for many clamp voltages. And then, for instance, you can look at the maximum value of the current during that experiment. And then you can make graphs as shown here on the right side. So you apply different voltage steps. In part, you change the extracellular concentration to assure that the sodium current is 0 at a particular clamp voltage to allow you to separate the currents. They use some other tricks as well, but this is the essential part of it. And then you can, for instance, make graphs showing the maximum current of, in this case, the potassium channel and the maximum current of the sodium channel. Now again, you see that if you increase the clamp voltage, which is on the x-axis, the sodium current increases, the maximum value of the sodium current, while the potassium current, while initially the sodium current increases with an opposite sign of the potassium current, and eventually it becomes 0, and that's exactly where the clamp voltage has the same value as the physiological Nernst potential of sodium, in this case approximately 40 millivolts. And if you further increase the clamp voltage, then the maximum current of the sodium channel becomes even positive. So sodium will temporarily flow out of the cell instead of from the outside into the cell. Now note that this is the value of the maximum current. It doesn't say anything about, say, the transient behavior. So for that, we will shortly discuss this little cartoon or analogy. So this is a cartoon of a channel that behaves as a persistent current channel. So in the light, the blue here, this is the channel. So this is the direction where the current can flow. And this is the gate. In this case, we call it an N gate. And in this particular example, the N gate is essentially closed at the membrane voltage of minus 60 millivolt. If we increase the voltage to minus 30 millivolt, then this process takes place. So the gate opens a little bit. And if we increase the voltage even more, to say minus 10 millivolt, make it less negative, then the gate opens more than in the previous case. So the finite position, the eventual position of the gate, apparently increases as the membrane voltage increases. And that's exactly how a typical potassium persistent current channel behaves. So once more illustrated, and now as a conductance as a function of the time. This is for 44 millivolts. So this position here, the gate opens pretty much to this particular value. And when it's 23 millivolts, it also opens, but a little bit less. The arrows have the same length. So this value is indeed a little bit larger at 44 millivolts than 23. For the sodium channel, it's very different. That's a transient current. It's essentially controlled by an activation, but also an inactivation gate, while the potassium channel only had an activation gate. And those are called M and the H gate. So what happens for the sodium channel that is initially at minus 60 millivolt and we change it to plus 20 millivolt? This happens. So the M gate opens and slightly afterwards the H gate closes. So there's opening of the activation channel and closing of the inactivation channel. And if you increase the voltage to another value, say plus 60 millivolt, then the M opens even more, but eventually the H gate still closes the channel. So this gives rise to a transient current. There is a particular moment in time where both gates are open and the current can pass through the channel. Now this can also be displayed in the curves we just saw for the potassium and now for the sodium. This is for 44 millivolts, 23 millivolts. So the maximum value is indeed a little bit larger here for 44 millivolts. This was the value that we've shown a few slides back. But eventually the channel closes. And the same applies for the 23 millivolt, but the maximum value is a little bit less. Now, Hodgkin and Huxley were able, based on data from the experiments, to describe this in a detailed form and actually in an equation that are shown here on the right side. So this is the activation gate for the potassium channel. And what is shown in this graph is the final position of the gate, which is normalized between 0 and 1 as a function of the membrane voltage. And it was shown that if this is the final position for the N gate, that if you take it to the power of 4, then you get a realistic behavior of the potassium channel. And that is shown here in the expression for the potassium current. So the potassium current is given by the maximum current, the maximum conductance, GK, with a bar, times the activation gate to the power of 4, times the difference between the membrane voltage and the Nernst potential of potassium. And this was essentially found based on experimental data, and this fitted the data best. For the sodium channel, we have two gates, an activation and an inactivation. So the activation gate, M, opens as a function of the membrane voltage, but the inactivation gate closes. So one is the opening state, it closes as a function of the membrane voltage. And if you take the product of M to the power of 3 times H, then you can describe the sodium current as a function of the membrane voltage. And please note that this is once more the values that are applicable when the membrane voltage has reached its equilibrium voltage. Of course, it takes some time to open and close the door, so there's also a time constant involved that I will discuss on the next slide. But the sodium current is given by the maximum sodium conductance times m to the power of 3 times H, and again times the difference between the membrane voltage and the Nernst potential of sodium. So you could use this for a current in the equilibrium state, but note, we just didn't discuss it yet, but we'll do in the next slide, that there's also a dynamic behavior of the doors. of the gates. And that's once more illustrated here. So it opens with a particular duration, and here this one opens and this one closes with a particular duration. That's not in the equation, at least not explicitly yet. So apparently there's a time constant, you can estimate them, that describes how fast the gate opens or closes. And for the N gate, the time constant is not really a constant, it is a constant that is a function of the membrane voltage as well, to make things more complicated. And this one, the dash curves, is for the potassium, for the persistent current channel, and the H and M time constants are for the sodium channel. And note that the time constant, for instance, of the activation gate is much smaller than the inactivation gate. And that makes sense, of course, and you can probably figure out yourself why that is the case. Now, if you combine all this information into the equation for the potassium channel, then we arrive at really a part already of the Hodgkin-Huxley equations that describe the dynamic behavior of the potassium channel. So the potassium current through the channels is given by the maximum potassium conductance times the activation gate to the power of 4 and the difference between the membrane potential and the rest potential, and the N is subsequently given by the change in N by this equation. That essentially tells you that the speed or the velocity of the change of the gate is given by the difference between its final position and its current position over a particular time constant. So if the time constant is small, it will reach its final position relatively fast. If it's large, then of course it's the other way around, and it's also defined by the difference between the current state and the final state, which is actually a very simple expression. The non-triviality is in the voltage dependence of the N and the tau. And we have a similar expression for the sodium channel, but then we have two gating parameters, an M and an H, and for each of them we have very similar expression with their individual time constants. So essentially these graphs and these equations describe in detail the dynamics of the sodium channel. And once more summarized on this slide. So in the case of the potassium conductance, we only have an activation gate, which is N, and in the case of the sodium conductance, there's an activation and inactivation gate called M and H respectively. And this, if you combine all this information, then we arrive at the Hodgkin-Huxley equations. So once more, the cartoon of their experiments and the action potential. And this is a simulation based on these equations. Note there's a very nice resemblance between the thick line here and the experimental data. And what's indicated here as well is the sodium and the potassium conductance as a function of time, and this is the current pulse that was applied to induce the action potential, and these are the full Hodgkin-Huxley equations. So, in closing, one more important comment, because I did talk about channels already a couple of times, but at the time of Hodgkin and Huxley, this wasn't known, that there were things like ion channels. It was thought or believed that something like that may exist in the membrane, but they had not been discovered yet. It took many more years before that had been proven to exist. At all the places where I mentioned channels, we should basically consider it a voltage-dependent characteristic of the membrane that, as was found out later, results from collective behavior of many, many channels, not of a single channel, as we will see shortly. So that for completeness of the discussion. I mentioned the word channels many times, but in fact, what I maybe should have said is that it is average behavior of many channels. Because if we would be able to look at a single ion channel, the behavior that we observe is essentially binary. A particular channel is either open or closed. And that was found by another beautiful technique known as the patch clamp technique, where it is made possible to measure ion currents through a very, very small part of the cell membrane. Recall that Hodgkin-Huxley used a very large part of the cell membrane with this relatively large electrode inside the axon. With the patch clamp technique, one is able to measure a very tiny part of the cell membrane and measure currents through that particular part only. And that is realized by a very small glass pipette. This is 2 micrometers. And if you put this onto a biological cell membrane, you can be lucky that in this opening there's only 1 or 2 channels. So, as with the voltage clamp used by Hodgkin and Huxley, the flow through many channels is measured, thousands. With the patch clamp, using a very small pipette, you can measure ionic currents through a very small part of the cell membrane only, and for instance only 1 channel. And if you would do that experiment, and that is possible, and this is a picture of how it looks, this is the pipette, this is a neuron, then this is the kind of current you would measure. So the channel is closed or open, closed or open. And the current through a particular single ion channel is very small. It's of the order of picoamperes. So this is a typical observation you can do when you do patch clamp measurements. So how does that relate to the microscopic currents? Well, as you can see already here a little bit, the channels are not open all the time, and the duration of the opening differs as well. So in fact, to come back to our discussion of the persistent and the transient channels, if we would do a voltage clamp experiment and at the same time we would measure with our patch electrode, with our glass electrode, the currents, then for this particular experiment, it is shown that during this voltage clamp, in this experiment, the channel opens and it closes, and the opening time is relatively short. If we repeat the experiment, then the channel opens a little bit longer and then it closes. Or it opens a little bit later, but it still closes. And this is another one, and another one, and another one. If you take the average of all these events, then we find the mean microscopic current. And indeed, this is the current of a transient channel. So the average behavior is shown here. And on a microscopic scale, the aggregate current, we would find this. So this is the many repetitions of the same experiment, the same channel. And if we have many channels, then we would observe this. And in this experiment, it's opposite. So we have the same patch voltage, and the ion channel, this is a single experiment, opens, and it essentially remains open all the time. This one opens a little bit later, but it remains open basically the rest of the time. And if we would take the mean microscopic current, we would find this curve, and the microscopic current would be this particular current. So this is the aggregate current. So clearly this is the current we would have for a persistent channel.